Okay. Hello everyone. Sorry I wasn't able to record this live this week. I had a mic issue. So I'm just going to do kind of a walkthrough of the special topics for this week. And then from next week, I'm going to try to just record it normally. Okay. So let's go ahead and get started. So yeah, this is the special topic section. And so to what we're going to talk about this week is sort of super sampling and anti-aliasing and how it's done in practice, sort of what the latest techniques are, things like that. So the first thing to kind of think about the motivation here is that supersampling is slow, right? So we can avoid aliasing by supersampling. We've learned about this and we kind of know how this can be done, and we're going to do it in Project 1. But it is kind of computationally inefficient, especially the higher and higher resolution you kind of want to get to, right? The buffer of stuff you have to store is much larger, requires a lot more bandwidth between graphics cards, displays, things like that. So the costs kind of add up quickly, right? And so the question we have is how can we get better images but at a lower cost? And there's a bunch of techniques that have come up throughout the years, and we're going to walk through some of those and see kind of what people have done. Okay, so first of all, the early solution, kind of the first solution, and this is something we learn about in class, is Mipmaps. So the idea of Mipmaps, it's not quite super sampling, but rather to solve aliasing by going the other way. So by reducing the frequencies in the stuff we're sampling. So when we're doing texture mapping, basically we reduce frequencies, sample from more blurry textures to kind of reduce some of that aliasing effect. Okay, and so this is one solution, relatively inexpensive because you pre-compute the mipmap and then you just use it. But so one thing to kind of keep in mind, the beginning kind of a lot of stuff. Okay. Um, then kind of after a while in about 2012, there was more work on actual anti-aliasing, right? And this was kind of a big improvement in anti-aliasing that was then kind of the state of the art for a little bit. So this is multi-sample anti-aliasing, or MSAA. And the idea here was basically, doing a texture lookup for every super sample point gets expensive super fast, right? Especially if we're super sampling 3 by 3, 4 by 4. It's a lot of points per pixel. And so the question is, what if we could reuse lookups within the pixel, right? And so this example kind of shows how this would work. And basically the idea here is that if we look at this pixel right here and this four set of super sample points, they're all contained inside the same triangle, right? Each of these four is all within this triangle. And so basically what multi-sample anti-aliasing will do here is say, well, since it's all in the same triangle, let's only do one texture lookup for all four. Okay, so this avoids 3 texture lookups that we would have otherwise had to do. Basically, this means this pixel is now almost as inexpensive as a non-anti-aliased pixel, right? It's slightly still more expensive because you still have to do the sort of in-triangle checks for all 4, but it's not nearly as expensive as if we had done 4 texture lookups, okay? So we've kind of won a little bit of efficiency here. On the other hand, if we have something like here in the right corner where we only have 1 pixel within the triangle, then we could still have to do up to the full 4 lookups if, for example, all 4 pixels were in different triangles or something like that, right? So there's no guarantee that a pixel gets any faster because of this, but we're basically just saying in this scenario where a single triangle covers my entire pixel, let's just kind of take a shortcut and speed that up, okay? But this isn't a perfect technique. The issue here is that you can still get aliasing within a triangle. So for example, if we had actually done all 4 texture lookups, maybe they're all slightly different, and when we average them, we get a slightly different color, whereas if we just take one texture lookup, we're sort of losing out on some of that detail, some of the high frequency variation in our texture. Okay, so that's multi-sample anti-aliasing, kind of the state of the art for a little bit. Okay, then in 2014 came another idea, temporal anti-aliasing, and this was a little bit different. Kind of, you'll see how it's a little different. Uses are a little different because of this. So the idea behind temporal anti-aliasing, and temporal means sort of in time, right? So the idea here is that we're only going to do one lookup per pixel, to kind of keep that efficient. But what we're going to do is instead of sort of averaging across space, we're going to average across time. Okay, so in each frame, we sample a pixel at a slightly different location. So then, one thing to note here is that because it's temporal, this is sort of much more this sort of works much better for like game engines or rendering movies, things like that, where you kind of have successive frames and you want to reduce anti-aliasing in all of them, as opposed to just rendering a single image. Okay, so basically what we do here is in each frame we sample a pixel at a slightly different location. So we kind of add a random jitter between 0 and 1 for both x and y, and so each frame we're sampling at a slightly different location within this pixel, and then we sort of average across the last couple frames to get an anti-aliased version. The idea being that, you know, if we don't have too much movement in the scene, or if we account for this movement, we basically will get multiple samples over time and get kind of a nice average, even though we only do one lookup per frame. So we kind of get both the efficiency and hopefully some of this anti-aliasing properties. Okay, but there is a potential issue here. So the issue is, well, what if there's high motion between frames? So what if, for example, kind of some object is in the frame 1 second and gone out of the frame the next second? We don't want, you know, the color from that object to kind of keep being averaged into our pixels. It'll kind of make it look like a ghost sometimes. You know, like it'll seem like it's slowly disappearing, things like that. It can make our image worse than if we had just done no anti-aliasing. So that's kind of a potential issue. And the solution to this in practice is that the pixel is just restricted to sort of the min-max of its neighbors. And in practice, it's not quite like the full neighborhood of 8 pixels, but just like the 4 pixels top, bottom, left, right. But the idea is basically that we take a look at its neighbors, the sample that we took from these neighbors in that one frame only, so not an average, just one frame sample, and say, well, if this color is too far away from that, let's restrict it down, let's clamp it down. Okay. And this is the technique that was used in Unreal Engine for a long time. They sort of put a lot of work into getting this ready to go in practice. And so, yeah, that's temporal anti-aliasing, kind of useful for game engines, rendering stuff. And you know, you could use it to render one image, right? But then what you would do is essentially have a bunch of frames over and over again rendering the same thing and just kind of sample at different locations, which could work, but it might just be easier to just do sort of regular supersampling, right? Okay, so that's temporal anti-aliasing, right? So kind of an interesting technique, 2014, used in Unreal Engine for a long time. And then next in 2018 comes kind of an entirely different approach, right? So up until now, we've sort of been, you know, doing all this. We're still kind of averaging across time and space. We're still sort of super sampling and filtering, that sort of thing, the traditional techniques for anti-aliasing. And then in 2018, sort of NVIDIA introduces DLSS, or deep learning super sampling. And the idea here is that, well, let's use machine learning models to sort of perform the super sampling, right? Machine learning and AI still kind of going crazy right now. So this is you know, a natural question to ask. And so the initial version, which came out in 2018, basically what it did, it was train a model, take in low resolution inputs, so 1080p aliased pixels, and then it would give it also a ground truth of a high resolution pixel, which they had rendered, you know, on a computer with large graphics cards, kind of taking a long time, rendering a whole data set, and then they would kind of, you know, pass this one image through the network, check the loss with this anti-aliased image, and then kind of keep training it that way. But some of the downsides of this initial one is that it needed to be trained separately for every game. So it was kind of very limited, required a lot of work just to get it to work on one single game, and sort of a kind of very introductory sort of model or tool, right? So that was that. It didn't work too well. You know, reviews weren't super great. But then a couple years later, they got a newer version, so the latest version, DLSS 2.0. This one now changed just slightly, so it uses both the low-res image, right, 1080p image, but also it uses motion vectors from this frame to past frames as input to the model. Everything goes through the model, we kind of get a new output, and it's compared to, once again, the same highly anti-aliased rendered ground truth, and then the error is propagated backwards. Okay. This model also works on all games with just one training, so it's a much more general model, doesn't have to be trained per game anymore, and has gotten significantly better reviews. Okay, so this technique is really kind of picking up. Okay, and then this is sort of the most recent, the last one we're going to talk about, is neural supersampling in 2020. So this is a very similar idea to DLSS in that, let's set up a neural network to kind of do this work for us. But there's more details shared. And this work was done at Facebook Reality Labs, and there's a link right here if you're interested in kind of reading more yourself. But here in the bottom is an image, and it's sort of the whole pipeline, right? So on the left we have the frame, so it takes the current frame, this is the one we want to upsample, and then it takes 4 frames from 4 past steps, the 4 last frames, okay? Then they sort of all go through this feature extraction step, this zero upsampling step, then the past frames go through this backward warping, some feature reweighting, and then finally there's this reconstruction network before we basically do some color adjustment and get it into our final frame. Okay, so there's a couple kind of steps here that maybe we don't know what to do yet. So feature extraction, zero upsampling, and this backward warping. So we're going to talk about that in a second. And then each of these on the right is sort of a architecture model for the colored boxes. So feature extraction looks somewhat like this, feature reweighting looks like this, and then the full reconstruction network looks like this. Okay, this architecture not super important, but if you're interested and maybe want to re-implement yourself or something, definitely take a look. All the details are in the paper. Okay, but let's talk about kind of what these things actually do. What does feature extraction, zero sampling, backward warping do? Okay, so some of the key parts. First of all, let's talk about zero upsampling. So zero upsampling is a very simple, the most simple upsampling technique, right? So first, a quick definition on upsampling is it's sort of taking an image and then taking it to a higher resolution space. So if I have a 4x4 image, I want to make it 8x8, want to make it 16x16, so on and so forth. And the way zero upsampling works is we do this, we have a bunch of pixels, we take them, and we essentially put them into one spot in the higher resolution image, and then leave everything else around it as 0. Okay, so it's essentially just kind of 1 pixel spaced out by the upsampling factor, and just all throughout the image. Okay, that's zero upsampling. Next, let's talk about backward warping. Okay, so just as a reminder, this is zero upsampling. Oh, and feature extraction, basically all they do is they take sort of this frame I, and then they extract a feature for every color and every pixel, and then they sort of propagate this feature throughout the network and use it in the future steps. Okay. So what backward warping is they take motion vectors from frame I minus n to frame I. So it might be the past frame, 2 frames ago, whatever. And then what they do is they shift these pixels forward. So they take kind of the motion vectors and they move the colors, move the pixels over, and then after they're shifted, they don't land exactly on the pixel values, so they sort of use a bilinear interpolation to warp it and get it looking sort of nice. So basically what they've done is they're trying to simulate the movement by taking all the pixels and shifting them by the motion vectors. Okay, that's backward warping. And then finally, feature reweighting is basically, well, after we do this warp, not all pixels necessarily are going to be good, right? So some pixels won't look good, some will be warped incorrectly, making the picture look weird, things like that. And so what this feature reweighting network does is it sort of learns weights for these pixels that tell us how much we should trust them. So low weight means this pixel has been warped weirdly and should not be trusted. Okay, and so those are sort of the key parts. And now let's take a look at an example. So here's the previous frame. So this is 4 frames ago. This is the current frame that we want to upsample. So this is the first step, right? We zero upsample it. So we take this frame and we increase the resolution, right? And then maybe it's a little hard to see over this video, but you can check out the slides or the paper. And so they basically have spread this out. And this is just a single channel, by the way. This is just one channel, but so they've spread this out, zero upsampled now. Now they do the warping, so they're basically taking the motion vectors, right? So for example, the motion vector for the nose would be kind of like here to here, the eyes would be like here to here, things like that, and then they sort of warp it, right? So you can see how the face it looks like it's shifted, the eye is kind of facing forward now, things like that. But at the same time, you notice kind of these artifacts all around here, around in the bottom corner, that make the picture look not so good, right? And then that's where this reweighting map comes in. So as you can see, a lot of the places where we have these artifacts are kind of dark on this weighting map, right? We're kind of zeroing them out, saying these pixels aren't good, don't pay attention to them. And then we reweight it. A lot of these artifacts are gone. and it looks much nicer. And then we can kind of pass this into our reconstruction network, and it'll take care of it. Okay, so this is kind of the walkthrough of what happens per frame. And then real quickly we can go over some examples. So here's some input output. You could take a look. For example, here in the window, it doesn't quite connect. The things don't go all the way across. Then you look on this side, it's a really nice, really good looking window. Similarly here, the plants look kind of fake. Over here, look really nice, right? And then another example, which I think is more kind of easy to see. Like for example, this light, you can almost see no details. You look over here, it looks really nice. Circular looks really good. The computer and all kind of much sharper on this side than on this side. Okay. So yeah, that's basically it. That's all I have for today. Kind of a little bit of an introduction into how, the latest in supersampling, anti-aliasing, how can we do it real time. And yeah, thanks for watching.